This lesson is going to be a continuation of the ideal gas law. I want us to first review our previous use of Dalton's partial pressures, talk a little bit about it before we go into another option for how to get the amount of a gas's pressure when it's something called collected over water. So let's deal with this first, and then we'll see the new topic. So it says a closed system with a volume of 2.0 liters contains radon gas and carbon dioxide, and the container is allowed to reach equilibrium at 300,000 300 Kelvin until the total pressure is constant. What is the partial pressure of radon if the total pressure is 1.03 atm and the carbon dioxide partial pressure is 1.00 atm? So again, we're going to be using our Dalton's law of partial pressures. So it says total pressure is 1.03 atm. It says that we're trying to figure out the pressure of the radon gas, which is R. If I could write, this would be great. Rn, pressure of radon, plus the pressure of the carbon dioxide. So 1.03 minus 1 is going to give me just 0.03. So then this says some helium gas is added to the system and the total pressure increases to 1.20 atm. What is the new partial pressure of radon? So gases cause pressure because they have moles of that substance, and those particles move around and bump into the sides of the container and cause pressure. That is the definition of pressure. And so you have to be really careful and read into the question. So it says a new partial pressure of radon if I added some helium gas. Well, I'm just adding more things to the mixture, but I didn't add any radon gas. So it's a trick question. The answer is still 0.03 atm because I didn't add any more radon. I added helium. So helium is going to have a specific pressure, but radon doesn't change its pressure. My total pressure did because the helium came in with and added more pressure on its own. So then it's asking what's the pressure of helium. So now my total pressure is 1.20 atm. We said on the last slide that your pressure of your carbon dioxide was 1, and our pressure of radon is 0.03. And now we're trying to figure out our pressure. If I could quit writing an R. My pressure of helium. So I'm going to do 1.2 minus 0.03 minus 1. And so my new pressure of my helium is going to be 0.17 atm. So this is like what we did last time. Now we're going to talk about when we collect a gas over water. So if a gas is collected over water, then you'll be given the pressure of the water at that specific temperature. The pressure of the water and the pressure of the other gas is going to give you your total pressure, which is the atmospheric pressure. So we're almost always going to know the atmospheric pressure. So in this one, it's different than in the previous one because in the previous one, we just added up all the totals and gave us the total pressure. Same concept, but our total pressure now is the atmospheric pressure. And so we will often be given your pressure of your water, and you're going to be asked for this, and you're given the atmospheric pressure. Your brain just has to know that that is talking about the total pressure. So this says 15.4 milliliters of hydrogen gas was collected over water on a day when the atmospheric pressure was 761.2 millimeters of mercury. The temperature of the water was 27 degrees Celsius. And it says the vapor pressure of the water was 26.7 millimeters of mercury. So here's the deal. millimeters of mercury is just a different pressure unit. It's a pretty common pressure unit that is used with this type of question. And so you are going to have to do a basic conversion for this one after you figure out some information. But AP is going to give you the conversion factor. So you just have to know how to convert from millimeters to atmospheres. So it says 15.4 milliliters of hydrogen gas was collected over water on a day when the atmospheric pressure was 761.2 millimeters mercury. So that is my total. So when we're doing our little Dalton's law of partial pressures, this number becomes my total pressure. It tells me that my pressure of my water at that point, because it's specific to the temperature, because obviously the higher the temperature of the water, the more water is going to turn into gases. So the pressure is going to be greater because the particles have mobility and can move around. So this one is 26.7 millimeters of mercury. And I'm trying to figure out what is the pressure of my hydrogen gas. So again, some basic algebra. I'm going to do 761.2 minus 26.7. It gives me that my pressure, I'm going to write it up here, of hydrogen gas is going to be equal to 734.5. But it asks for it to be in atmospheres. So I'm going to do a basic conversion. Any unit I start with here, I have to cancel with on the bottom. So when it talks about pressure units, AP's reference sheet will tell you that 760 millimeters of mercury is equal to 1 atmosphere. So you just have to work this basic conversion out. So I'm going to do the 734 divided by 760. I don't use anything in the ratio for rounding. And so my final answer in atmospheres is going to be 0.9664 atmospheres. Then my second thing says how many moles of hydrogen were collected. Well, now that I know my pressure, I also know my volume, and I know what the temperature was. So I'm going to switch over. Anytime it talks about moles, that means I'm probably going to be using, and about gases, means I'm probably going to use my ideal gas law. So in this one, my pressure is 0.9664. My volume is in milliliters. You have to get really comfy with shifting between milliliters and liters. That's a really common conversion. So you're going to take 15.4 divided by 1,000. And so it's going to give me 0.0154. I'm solving for my number of moles. I'm going to use my gas constant. And my temperature is 27 degrees Celsius. I'm going to add 273 to it to get 300. But weird thing is when you add numbers together, it's actually 300 decimal because this number actually goes past to 0.0. And then I add the 273 to it. So it makes my ones place to be significant. So it's actually 300 decimal. So then mathematically, I'm going to do 0.9664 times 0.0154 equals divided by 0.08206 equals divided by 300 equals. And I need to convert it, my final answer, to 3 sig figs. And so it's a really small number. Because I'm starting out with some small numbers in the first place. So your calculator may give this number to you in scientific notation, and that's fine. Or it might give it to you just in normal form. So mine gave it to me in scientific notation, which came out to 6.05 times 10 to the negative fourth, or that would be 0.123605. Either of those answers are correct. This one is in scientific notation. This one is in normal form. Both are acceptable by AP. Both have the correct number of significant figures. Then my last question says, how many grams of hydrogen was collected? Well, this is just some basic math. This is just going to be a basic mole to gram conversion. So I'm going to do 6.05 times 10 to the negative fourth moles of hydrogen. And then you have to be careful because hydrogen is always diatomic. You'll notice I'm writing it as H2. And so it's going to be the mass of hydrogen, so 1.008 times 2, and that gives me 2.016. And then I'm going to multiply that by my 6.05 times 10 to the negative fourth. And my answer comes out to 0.00122 grams of hydrogen. So this is how AP often does their FRQ questions. They'll ask you one thing that leads into another thing that leads into another thing. So this whole question is about gases, but it's challenging your understanding of three different concepts. It's challenging your understanding of what is pressure being collected over water. It's challenging your understanding of ideal gas law, and it's challenging your understanding of basic mole conversions. So if the Kelvin temperature of a gas is tripled and the volume is doubled, the new pressure will be what? So this is saying that we need to figure out what the pressure is. So my equation is PV is equal to nRT. I have found that these questions are easiest if I rearrange my variables, not plug in any numbers, but just rearrange the variables to solve for what I need to. That's a math option you always have for any of these equations. I often plug and chug into equations, like back here. I plugged it in and solved it out, but I could have very well set it up as N is equal to PV divided by RT. I could have set it up like that before I solved it. And that's what I recommend on problems like this that are asking about fractions. So I need to know what the pressure is. So to solve for my pressure, it's going to be nRT divided by V. That's how we're going to solve for pressure. And so this is saying that I tripled my temperature, which means this is 3 times whatever it was, and I doubled my volume. And so if I set this up, the fraction I end up with is 3/2. And so it's going to be 3/2 the original pressure. So if you rearrange that variable and then just plug these numbers in, it'll typically get you to the answer that you need to. And for me, it's easier to use this math equation other than thinking about numbers. You don't actually have to plug anything in. We're just looking at a ratio. So then the last topic that goes along with ideal gas law is the concept of volume stoichiometry. And so with volume stoichiometry, you can use the coefficients for liters the same way that you can for mole ratios. So remember, stoichiometry is where we have a balanced equation and we use our mole ratio to shift between one substance to a different substance. So anytime you do anything with stoichiometry where you're shifting from, like this one is giving me my information in water, but it's asking for my information in oxygen. If I have to switch substances, I've got to have a balanced equation to do that problem. And so in this one, I've got to balance this equation first. So right now I only have 1 oxygen here and 2 here. So I'm going to put a 2 in front of that. That gives me my 2 oxygen. It also gives me 4 hydrogen. So I'm going to put a 2 in front of that. And then in front of this is an understood 1. So how many liters of gaseous oxygen are needed to produce 4.00 liters of gaseous water if both gases are being measured at STP? So it is going to be a really basic one-step conversion. I'm starting with water. If I start with water, I have to cancel with water. And I'm going to use these numbers as my liters because these coefficients can represent more than just moles. So it is going to be 2 liters of H2O. I'm trying to get to oxygen. That's my unknown. That's what I'm solving for. So it's going to go on top. And in front of oxygen is an understood 1. So I do 4 times 1, which is 4, divided by 2, which gives me 2. But I need sig figs, so it'll be 2.00 liters of O2. And that's it. If it's asking you just go from liters to liters, you just use these coefficients to be able to do the conversion. So this is the same equation. I'm going to go ahead and balance it out again. How many grams of water are produced if 4.75 liters of oxygen were used at 122 degrees Celsius and 0.997 atmospheres, assume the gas is ideal? So this is a lot more information than what we were given in the last one. If it says assuming gas is ideal, or if it gives you all kinds of variables, it's indicating you need to use the ideal gas law. So let's use our ideal gas law. So I'm going to do 0.997 atm times 4.75 liters. I cannot solve for grams using ideal gas law. I can solve for my moles. And my temperature is 122 degrees Celsius. I cannot leave it at Celsius. I got to add 273, and it comes out to 395. So then I'm going to do 0.997 times 4.75 divided by 0.08206 divided by 395. And that information comes out to, and this is going to be my number of moles of my O2. That's a big thing to understand, is all this information is talking about oxygen. So this is my number of moles of O2 is going to come out to 0.146. Once I know that, then I can use stoichiometry to convert. So if I know moles, then I can convert over. I'm going to have to use a mole ratio this time from up here. So I'm going to do 1 mole of O2 on the bottom. I'm trying to get to water, so I'm going to do 2 moles of H2O. Then on the bottom is going to be 1 mole of H2O to my grams of H2O on top, which is 18.016. This comes from the periodic table. I add 2 hydrogens and 1 oxygen. So then I'm going to mathematically calculate it out. And I need 3 sig figs. And so my grams is going to come out to 5.26 grams of H2O. So first I had to use my ideal gas law, and I solved for my moles of O2. Then I had to do conversions to get to my grams of H2O. So again, I had to use stoichiometry, but this one was different than my previous one. It just depends on what's given and what it's asking for. So on this section, we learned about dealing with stoichiometry. We also learned about dealing with a gas being collected over water. It's a little bit different. It's still Dalton's partial pressure, but it's a little bit different.